Hello everybody. So here we are back with another video, and I think that new video, new topic. If I scroll through what I have to show you for this video, um, then it would look complicated, like a lot of new things you learn in math. So look at all the symbols and formulas and charts and graphs and all that kind of stuff. So it does, at a glance, if you looked at everything I need to show you, like all in one burst, then it would look complicated. But I think you'll find this real easy because if you learned what we already learned before about confidence intervals, if you learned that okay, and you understood it and you felt like you could do that, then I don't think this will be that hard, even though it might look intimidating at first. Okay. Now I need to, whenever we do math, we learn to solve a certain kind of problem. Okay. And so first I need to summarize what problem we're faced with that we're going to try to solve. Okay. So I'm going to kind of reuse an example that I used before when we were learning about confidence intervals. I want to say that suppose that there's a population, and let's say that the population is all house cats or something like that. It could be all house cats in our city or in our neighborhood or in our state or in the world, whatever. All right. That's the population. And maybe we want to know something about the population, such as the average weight. Okay. And let's say that like we don't know anything about the population. We don't know what the average weight is. We don't know what that standard deviation, like, whatever other numbers you can think of. Let's just say we don't know. Okay, so there's this population, house cats, and we don't really have any knowledge or information or numbers about that population. So what do? We take a sample from that population. Okay, so first, that's the difference between a population and a sample. All right, the sample comes from the population in order to know something about it. All right, so we take a sample, and the sample has to be of a certain size. Let's say we take 40 house cats, and we do some math. Let's say maybe we weigh them all. Maybe somebody in the veterinary sciences is doing this research or something like that, and we weigh all the house cats and we say, okay, well, we weighed them all and we calculated the average, the mean weight was 9.8 pounds. Okay, so we weighed them all, we added all the weights together, and we divided by 40, and we got 9.8 pounds. And let's say we also did the calculations on the standard deviation for the sample. That was 1.2 pounds. Let's suppose that we did all that. Okay, now what does or what can this tell me about what I want to know? Because what I want to know is what is the average weight of a house cat, all right? So maybe they're developing some kind of veterinary drug, some medication, and in order to market the dosage correctly, they need to know about how much does a house cat weigh or something like that, all right? Okay, I want to know that. I want to know what the average weight of a house cat is. And how can my sample of 40 house cats with the mean and standard deviation calculated tell me that? All right, so that is the problem. That's the question that we're going to explore today. Okay, now, real quick. So there's some fine print about this. And one thing is the sample must be random. Like, so when you're trying to study the population of house cats, and you take a sample, you can't take the cats that are the cutest or something like that. All right, or the cats that are the friendliest, whatever. It's like every cat in the population has to have an equal chance of being selected at random. Okay. So and I mention that just because it might be in some examples you encountered that it says that a random sample is taken or something like that. All right. And so, yes, the sample must be random. Now, okay, I wanted to give you an outline of how we solve that problem, because so far I've just told you this is what I want to do. I want to find out, what's the mean weight of a house cat? What's the average weight of a house cat? Here's how we do this in the situation when there's a population of some kind that we're studying and we don't know the mean of the population, which is signified by the Greek letter mu, or the standard deviation of the population, signified by the Greek letter sigma. Okay, now let's pause for a second. The last section for our last test was like this, but the standard deviation of the population was known. And that might seem kind of weird because you might think, well, how could, like, you're trying to study this population and you're telling me you don't know the mean, but you do know the standard deviation? Like, how does that happen? So that's a little weird, and that's a kind of a contrived problem. But this is more realistic, where we just don't know anything. Like, I don't know the mean and I don't know the standard deviation of the population, just like up here. House cats, I don't know the average weight, and I don't know the standard deviation weight either, okay? Okay, so what do? We take a sample, and it will have size n from the population. We calculate the sample mean, and maybe it's given to us, maybe we calculate it. The sample mean, as opposed to the population mean, sample mean is given by the symbol x bar, x with the line on top of it. And the sample standard deviation, S, okay, as opposed to sigma for the population standard deviation. All right, so we take the sample, we calculate, or we are given the sample mean and the sample standard deviation. Now here's what we'll do. We'll construct a confidence interval for the population mean. And that will be like a statement that says, well, average weight of a house cat, I don't know, but I'm 90% confident it's between this weight and this weight. That's what a confidence interval is. Could be 90%, could be 95%, like whatever confidence level you or somebody else wants, okay? So there's our formula for the confidence interval, okay? Now we'll have to like dissect this formula. There's lots of different variables in there, and I'll have to show you how you calculate each part of it. But what you do is you take x bar, which is the the sample mean, and you subtract or add this number called the margin of error. Okay, so margin of error is t subscript c, tc, times s, the sample standard deviation, divided by root n, where n is the sample size. Now, so s is given, or found, or calculated. It's the sample standard deviation. N is likewise given. It's the sample size, right? X bar is given or known. It's the sample mean. But this number t with the subscript c right there, that's a number we find from something called the t-distribution. And StatCrunch makes this really easy to do, okay? If you could just kind of not be intimidated by the formulas, StatCrunch will make this so easy, okay? StatCrunch and maybe like a handheld calculator, or some kind of calculator, however you want to do that. All right, so let's do an example. First, we need to learn how to use the t-distribution. So see that number t with the subscript c that the confidence interval is calculated from? Let's focus on that first, okay? So it says find the critical value t subscript c for a confidence level of 99%, 0.99 would translate to 99%, sample size 17. Now, when we use the t-distribution has this thing called degrees of freedom, okay? Which I think is a complicated mathematical idea. I can't really think of a simple way to explain it. I'm gonna take the risk that you're not really that interested in it anyway, okay? But a t-distribution has this thing called degrees of freedom. So what you do is you use StatCrunch to calculate with a t-distribution with n take away 1 degrees of freedom, n being the sample size. So that'd be 17 minus 1, which is 16 degrees of freedom, okay? And this number here, which it has its opposite over here, is this number t with the subscript c. And if you want, it means that for a 99% confidence interval, 99% of the area under the t distribution curve is here, okay? You use StatCrunch to do that. Let me show you. So I'm going to access StatCrunch. I'm going to use 16 degrees of freedom and set it up such that it shows me where 99% of the area is, and then identify this number, okay? So I'll go over here. Here's what we do. First, we open StatCrunch, which we can do from the problems on MyMathLab calculators. Then see right here where it says t. Okay, that's what I want. So it opens the t distribution. Now we said 16 degrees of freedom, okay? Oh, I need between, okay? Because like this number is t subscript c, and this number is negative t subscript c. So there was 16 degrees of freedom, and I wanted 0.99 as my confidence, or 99%. And I compute it, and there's my number. It's like, that's 2.9208, and that's negative 2.9208. That's like 2.9208 is my number, okay? All right, so I have it. You saw how I use StatCrunch, and I'll say, whoops. Well, I found TC is 2.9208. All right, so that's just that number. Now, I'm not doing everything at once, okay? I'm just focusing on one part of this formula at a time. All right, so that T subscript C, that's how you find that. Now, let's take this a little step further. Like my point, or my ultimate objective, is to tell you how we can say something about the weight of the average weight of a house cat based on our sample, okay? But we're not quite there yet, so let's do this. Let's say, okay, next thing, how do you find the margin of error? Okay, now, so this would be an 80% confidence level, a sample standard deviation of 4, and a sample size of 23. So first we use the t distribution with n minus 1 or 23 minus 1 or 22 degrees of freedom, DOF, degrees of freedom. We find TC from that, and then if we consult my formula up here, you know this, that's the margin of error. It's TC times S, the sample standard deviation, over root n, the square root of the sample size. Okay, so well, let's do that. I'm going to open my t distribution again, and I want 22 degrees of freedom and 80% confidence. So let's see. 22 here. See, DF is degrees of freedom, and 0.8 for my confidence, and I get 1.3212 for my critical value TC. Okay. All right, so let's see. I'm going to write that down here. TC is 1.3212. All right, am I remembering that correctly? 3212. Okay. So now I would need to do this. Objective, this problem, calculate the margin of error. So let's see, we'll do 1.3212 times S over root n. So that'd be 4 over root 23. Okay, so now I will use my handheld calculator. 1.3212 times 4, okay? And when I do this, I calculate that result, times 4, okay? And then I divide that by root 23. And that's how I would do it on my calculator. I don't have a fancy calculator, but you know, that's how I would do it on this one. You might use your calculator slightly different, and if you're not getting your answers right, you might ask me about that so we can sort out how you do this on your calculator. Anyway, so the number I get when I do that is 1.10196. Okay, so there's my margin of error. Now that number has some rounding to it, but as you've seen, the problems on MyMathLab will say like round to the nearest 10th or 100th or 1,000th, who knows? Just like you calculate and then you round however it says to round. Okay, so like first, with the overall objective being to find the confidence interval, we find this critical number, TC, from the t-distribution. Then we find this margin of error. Okay, now if we go one step further, we'll find the entire confidence interval. So here it goes. Say problem goes like this. Calculate a confidence interval for C is 0.9, so that would be 90% confidence. X bar, the sample mean 14.7. S, sample standard deviation 3. N, sample size 8. Okay, all right. So that would translate to be 90% confidence on my t-distribution with what's one less than 8? 7 degrees of freedom. Okay, so let's start there. 90% confidence, 7 degrees of freedom. So I'm going to open my calculator on StatCrunch again. 7 degrees of freedom, 90% confidence. That's how I would put that in. 7, 0.9, 90. And it says 1.8946. Okay, that's my critical number right there. 1.8946. So that is, this TC number. All right. Now look what I'm going to do next. 1.8946 times 3 over root 8. Why is that? Well, from this critical value TC, which I just found, 1.8946. Always feel like I forget one of the numbers. Okay, 1.8946. I take that and I multiply by the sample standard deviation, and then I divide that result by the square root of the sample size. So my margin of error would be 1.8946 times 3 over root 8. Well, let's see what that is. Okay, 1.8946 times 3 divided by root 8. Okay, so I get like 2.0095. All right. So I'm supposed to take my sample mean, 14.7, and either subtract or add that margin of error right here. Okay. So let me write down that number, 2.0095. Okay, and there's more digits after that. I'm going to leave it in my calculator, but I wanted to write down so you could see it. So I'll take 14.7 and I'll subtract that number, and I'll get 12.690. Okay, so that right here, 12.690. Okay. And then, let's see, I take X bar, 14.7, and I add the margin of error, which is 2.0095, okay? And I get 16.709. I actually get 16.7095. All right, so that's my number. Now, try those calculations as you're watching the video. Make sure that you can get them. I found the critical value. From that, I find the margin of error with this formula right here. Okay? From that, I take this number, and that's E, that's the margin of error. I take the sample mean and I subtract it. I get 12.690, and then I add it to the sample mean. I get 16.7095. All right. So my rounding is a little sloppy there. but I guess I'm more concerned that you see the process. Okay. All right. Now, so we took this one step at a time. First, we learned what the t-distribution was. Calculate TC, then calculate margin of error, then calculate confidence interval. Okay, so let's do then the problem that I started this video with about the cats, the mean or average weight of a house cat. So it goes like this. If I were to like verbalize that question the way you might see it when you're doing your assignment. Suppose we want to know the average or mean weight of a house cat. So we take a random sample of 40 house cats. Sound familiar? Yeah, that's the way I posed this problem from the beginning, right? Okay. And from that sample, we calculate the average or mean weight to be X bar as 9.8 pounds and a standard deviation for the sample of S is 1.2 pounds. Can you calculate a 90% confidence interval for the mean weight of a house cat? Mu, given by the Greek letter mu. Okay, well, so first we would consult the t-distribution with 39 degrees of freedom because the sample size is 40, okay? And we want a 90% confidence. So I use those two numbers to get my initial value from the t-distribution. 39 degrees of freedom, 90% confidence. Let's go there. 39 degrees of freedom, 90% confidence, and there's my critical value of 1.6849. Okay, so let's see. I used that 1.6849 to do my calculations for the margin of error like this. 1.6849 times 1.2, the sample standard deviation, divided by square root of 40, where 40 is the sample size. Okay, so I'll do that like this now with my handheld calculator. 1.6849 times 1.2, and then divided by root 40, okay, and I get 0.3197, okay, so that's the number I'm going to give you. 0.3197. All right. From there, I build up that confidence interval. I use the margin of error. Why does it say 9.8 minus E on one side, the low end of my estimate, and 9.8 plus E, the high end of my estimate? Well, because 9.8 is the sample mean. And to make the confidence interval, you take the sample means minus the margin of error, which that's the number we just found. That's the low end of our estimate. And 9.8, the sample mean plus our margin of error. That's the high end of our estimate. That's how you make a confidence interval. So I'll take 9.8 and I'll do what I just told you, minus 0.3197. All right, and I'll get the low end for my estimate to be 9.48 pounds. Okay, I'm going to put average weight like this. And then on the high end of my estimate, that'll be 9.8 plus 0.3197. That's going to be 10.12 with some rounding. And this is pounds, and this is pounds. Okay, all right. Now, well, what does that mean? I have to say, maybe I built this up too much, because it's not possible from this to know for certain what the average weight of a house cat is. Like, that's not the way things work in probability and statistics, okay? Probability and statistics deal with things that we could only know with a certain percent confidence. That's why it's called a confidence interval. So what that means is that, well, I still don't know what the average weight of a house cat is, but I'm 90% sure that the average weight is somewhere between 9.48 pounds and 10.12 pounds. So at least I narrowed it down, right? And that's, the most that we can do in a discipline like statistics. Okay, I can narrow it down. I can tell you how confident. I can tell you what the probability is that I'm right. I got a 90% chance of being right about this, that the average weight of a house cat really is between 9.48 and 10.12 pounds. But that's as far as we can take it. Now, there are some refinements from here. The larger the sample size, the more this confidence interval will squeeze smaller and smaller. Like if this was too big, if that didn't narrow it down enough, we could collect a larger sample and repeat the process. So there are ways that you can improve this if it's not good enough. But, like no matter what, a confidence interval will just narrow things down for you and give you a probability of being right.